Welcome back, Chemistry 30. This is the EQ1.4 section in the equilibrium unit, and it deals with heterogeneous equilibrium. So in the last section we looked at the equilibrium constant, looked at the size of the equilibrium constant. Now we look at what is included in the equilibrium expression and what isn't. So write the equilibrium expression for the heterogeneous reaction, explain why solids have no effect on equilibrium constant, etc. So many equilibrium involve substances that are in the same phase. So all gases, all liquids, that's what we mean by that. Usually gases or liquids. Such equilibria are called homogeneous equilibria. In some cases, however, substances are in different phases. That is referred to as heterogeneous equilibrium. So for example, consider the equilibrium that occurs when solid lead 2 chloride is dissolved in water. So it's a solid, it's dissolved so it breaks up into ions, 1 lead, 2 for every 2 chlorides. This system consists of a solid equilibrium with 2 aqueous species. If we want to write the equilibrium constant expression for this process, we encounter a problem we have not encountered previously. How do you express the concentration of a solid? Because remember, concentration, or molar concentration, C equals N over V, it's the number of moles of solute dissolved in so many liters of liquid. Well, how do you present a solid in a solid? So although we can express the concentration in moles per unit volume, it's unnecessary to do so in writing the equilibrium constant expressions. So key thing to note here, whenever we have a pure solid involved in a heterogeneous equilibrium, its concentration is not included. So we're only concerned about aqueous substances or gas substances. The concentration of solids and liquids are essentially constant. Thus the equilibrium constant expression would just simply be products over, well, we don't include reactants. So lead times chloride because there's 2 chlorides, so it's simply that. So even though lead chloride does appear in the equilibrium constant, even though it's in the equation, it does not appear in the equilibrium expression. It must be present, though, for equilibrium to occur. So why are solids and liquids excluded? The concentration of pure solids or pure liquids have a constant value compared to gases. And I have kind of a gross example here. If you imagine a dog doing its business on the floor, you can see that solid on the floor and it doesn't change, and yet it doesn't take much time for the concentration of gases in the air to change substantially. So the gas concentration changes, but you still see that solid on the floor that you have to clean up. If you look at liquids, if you spill a bottle of really strong cologne, you can see that liquid sitting on the ground. It doesn't seem to change much, and yet the gas concentration would change substantially. You'd be able to smell it, and depending upon the cologne, it may be a good or bad smell. So if we look over here, example, if the mass of a solid doubled, its volume also doubles. The concentration, which relates to the ratio of mass to volume, stays the same. Since equilibrium constants expressions include terms only for reactants or products whose concentrations can change, then we don't include the solids or the liquids. Okay, so the species have to actually change to be included in there. Okay, if we look at the next page, the illustration on the right represents the following equilibrium. Calcium carbonate, and this should be a little equilibrium sign, not equals. Solid calcium oxide and carbon dioxide gas. The first bell jar making a closed system has a large amount of calcium carbonate in it, as we can see, and a small amount of calcium oxide and a certain gas pressure due to CO2 floating around. Second bell jar closed system has a small amount of calcium carbonate, a large amount of calcium oxide, and a certain gas pressure as well. The gas pressure due to CO2 is the same regardless of how much CaCO3 we have in that system at equilibrium. So again, if you look at over here, having solids doesn't change. It's the gas, it's the CO2 gas that would change. So products, it's just simply that. We wouldn't include this and we wouldn't include this because it's solid. their presence does not change in terms of concentration. So in summary here, if you take a look here, we should like to put a star beside each of these. Substances in the gas or aqueous phase are included in the equilibrium constant. Because when you dissolve something, its solubility changes. The amount of dissolved material changes. Or gases, the amount of gases in an air can change. Whereas solids and liquids, their concentrations don't change much compared to these. Therefore, they are not included in the equilibrium expression. So, going with that, if we just simply write the equilibrium constant expression for each of the following. So, Kc or Keq, call it whatever you want. Just don't call it lonely. So over here we have products. So, gas, liquid we don't include. Gas we include. Gas we include. So CO over CO2 multiplied by H2. Maybe pause the video, see if you can do the next few. There's one here, plus there's two on the next page. So maybe pause the video right now and just simply see if you can figure out what it would be. Okay, if you had time to do that, let's take a look here. So gas, solid, gas. So the equilibrium constant expression, there's two CO2s, so multiplied by each other, and two COs on the bottom. So there you go, that's how you do that. Okay, if we look at the final one on the next page, KQ or KC, it doesn't matter. So aqueous, solid we don't include. Solid we don't include. Aqueous we include. So chromium 3 ion, concentration, again the square brackets means concentration of. C equals N over V, the amount of material dissolved in a volume of solution. And then silver ions, there's 3 here, multiplied by themselves, there we go. And the last one, let's see, solid gas, solid gas. So H2 to the 4, all over H2O to the 4. That's it. So you should be able to do the assignment. The assignment is just as easy. You should be able to get through that fairly quickly. All right, see you again.